Thank you for watching Knowledge Academy. Okay, in this lecture, we will be talking about potential energy and conservation of energy. So there is a two thing. Potential energy is basically another branch of energy, and we're going to be talking about conservation of energy and what is the whole concept of conservation of energy workout. So first thing first, we're going to be talking about potential energy. And if you remember, we call about energy is nothing but is your capacity or tendency to do something. If tendency means if you have capabilities, you are willing to, you can afford to do something. Energy wise, you can afford to do something, that is energy. Then we learn about kinetic energy. Okay. In this kinetic energy, we talk about kinetic energy is nothing but something is start when object start moving, the energy produced in the object because it is start moving as more and more it move it more and more faster it move, the kinetic energy keep going up and up. Okay. Now if I'm saying if I things are keep start moving up and up, it means let's suppose you start your car, right? You start your car, car have an engine. And what happened when you start the car, the velocity is zero, and you start the car and push the gas. And what's happened when they push the gas pedal, car start moving and velocity increase from zero to whatever 10. If you push the gas much harder, the velocity may be going to 20 meters per second. And this is where things are keep going on and on. Okay. Now, when we have a different way to look into this scenario. The first one is when car start, engine start, engine basically taking the energy from the fuel tank. And let's suppose this fuel tank have 20 gallons of fuel. As soon as you start the car, you start burning fuel, and fuel actually going down from 20 to 19 gallons. Right? I'm just giving example, so make up some numbers. You're burning fuel, and car start going from zero to this velocity. So this energy, which is called maybe called fuel energy, goes down, and some energy goes up, and that energy is kinetic energy. And that is a formula we learn about kinetic energy. Same concept is going to work in a potential energy. So potential energy is that if you want to move something up, right? Let's suppose you have a object and a person coming here. You want to lift the block, and then he's going to lift the box from here to this location. So I'm going to be just putting some points here, point A, point B. And this whole example, I'm talking about potential energy. Right? We discussed kinetic energy earlier in detail. Now today is our goal is to talk about potential energy in detail. And now the whole mechanism is when you move this, or this person is going to move from this object from he try to lift from here, pretty much A is the same level, and it's going to move from here to there. This distance is called D. So this person moving this object from this location, right? And since I'm going to erase the A because A pretty much look like in this location. So it's going from A to B, displacing D. So he's applying force upward, and distance is D. So total work is done by this person is equal to force times D. And we also learn about that the work done is also a energy. Or basically I'm saying, I'm going to say here, the amount of energy, the energy lost by this person is equal to the energy gained by the block of this box, gained by right. So how much energy this person lose? This person lose actually, this person did the work, so it actually lose the work. He did the work. So how much work he done? This work equal to FD, right? If I'm gonna say this person is done FD. So really, if I'm gonna write in another way, I'm gonna write, say this person is done FD work. And if you want to elaborate more better formula, you're actually writing in this way, you're writing it into more intuitive way, which is F equals to F times D cos theta. Usually people don't use this cross, they just use FD cos theta. And what is a theta? Theta is a distance, or theta is the angle between force and displacement, direction. In this case, force is up, displacement is also up. So D is up, F is up, both in the same direction, so theta equals to 0 degree, means they are in the same direction. Anyway, since this is, we're talking about the person side, so let's talk the other side. The other side is how much energy gained by the block or this box. This energy should be equals to this, the work is done on the block, it should be equal to the energy gained by the box. Now we're gonna call this energy, since it is done by against the potential, the gravity, I'm gonna call this energy a specific kind of energy, and that energy called potential energy. So really, if I want to be writing this thing over here, I'm going to say that the potential energy equal to, in this case, equal to, I'm going to call PE, means potential energy. Usually we use this one, must be equals to force T cos 0 degree. If I do 0 degree, is going to be equal to force times T cos 0 means 1. So I'm going to be writing 1, but usually 1 doesn't make any change. So I'm going to eliminate the 1, simplify my equation. And then I'm going to be writing here FD. This force equals to the weight of the block, right? Because when person try to lift the block or this box, he's supposed to be applying same force. How much is the weight of the block? And what is the weight of the block? W equals to mg. So I'm going to be writing here W equals to mg. So I'm going to replace this force with this and give some reason in the front. This force being replaced by mg, and d is d. Now I'm going to write here, since W equals to F and W equals to, so that is the reason I'm using to eliminate this. And really, this is my PE formula. Typically in your book, you write in either this formula or this formula, MGH. Both formulas are common. All we have is potential energy equal to mass times G. G is 9.8 meter per second square. And H is a height, how much you, 2 meter, 3 meter, whatever we're going to be putting. Yeah. Now, this is what we're going to be talking about. And this is the whole concept is there. So let's continue this potential energy and moving forward to the next topic. What does that mean? It means the total energy of the system remain unchanged. Right? And when I say mechanical energy, means mechanical means mechanics, things are moving, machines. So I'm going to say the mechanical energy initially of the system must be equal to the mechanical energy final stage of the system. It is only possible when there is no friction in the system, no friction. the system. Example I have, let's suppose if I have a inclined plane, like this kind of plane, and I have a block, and I put the block here and release. When I release the block will start moving downward here. So block was here early, and in the end block was ended up here. So this change in height, I can call it h. Maybe I can give some number. Just for this example, I give some maybe 3 meters. So this block was at A position and it go to B position. And how much change? The height is h. The block was here. Velocity was 2 meters. The block, when you release the block should be 0. Block should be releasing by release the block 0 meter per second. Why? Because you release them. So when you release things, it's stationary. But when the block comes here on VB, so this is VA, or VB equals to, I get 3 meters. So I have two things going on. Number one is when you release the block, the kinetic energy, which is the energy of motion, was equal to 0. When block comes to B point, kinetic energy increase. Kinetic energy increase going up from 0 to something, and the formula is half mv squared. Remember, energy does not come for free. If something, one energy goes down, some other energy goes up. If one energy goes up, it means another energy goes down. And that's the whole phenomena here. So it looks like total energy of the system is similar, but something happened here, something happened here. Both things are balanced, but one thing going up here, one thing going down here, one thing going down here, one thing going up here. That is the transformation between kinetic and potential energy. Okay? That is what you call mechanical energy. So I'm going to be writing like this. So kinetic energy, I told you, let's talk about the PE, potential energy. Potential energy at point B is 0 pretty much, or lower, right? Lower. But potential energy at point here at H is higher. So I'm going to say that potential energy here at this point, point A, PE is high, KE is low. At point B, KE is high and PE is low. It makes sense? So KE goes down when PE goes up, when PE goes down, KE goes up. So it's basically a trade-off. So I'm going to be writing this. KE I, kinetic energy I, plus U means potential energy sometime, GI, potential energy, equal to KEF UGF, right? And if I want to substitute the values here, I can substitute here. The values is going to be, the formula of this is going to be half mvi squared plus mghi. I means A is initial point, this is F. And potential energy is half mvf squared plus mghf. Final point, initial point, we can substitute the values, we can get. Now the thing is, one thing you notice, this is called mechanical energy. Initially, this is called mechanical energy. Final, you notice one, both should be equal all the time. And this formula only apply, if no friction in the system. What does that mean? It means this system doesn't have any friction, it's sliding frictionless. It's a frictionless system. The next topic we have is reading the potential energy curve. And what does that mean, reading the potential energy curve is? Right? Potential energy actually can be increased and decreased. So if you have any motion like this, let's suppose you have a roller coaster. So what you're gonna do, you're gonna be trying to draw the potential energy curve. So when roller coaster start, potential energy is high. When roller coaster goes down here, potential energy goes down. So you're gonna basically making a potential energy curve. And it's telling you if you want to draw inside a scale, maybe this energy is 10 joule, right? Energy unit is joule, here energy unit is 7 joule. At this point, energy may be 8 joules, here maybe put up maybe 8.2 joules, and here the energy may be 11. So you get different values of energy, and then the same thing you can get it into different location. Okay? This is a simple concept for energy curve. Let's talk about work done by an external force. Work is done by an external force. What does that mean? It means initially I say there is a frictionless system. We assume initially, we assume frictionless system. It means no friction. But is that real? Not really. In reality, we have friction. What does that mean? It means you ignore cannot ignore the friction when you're talking about. But in reality, we have a friction. So it means there's another theory. Since friction is a force, friction is a force. Now think about it. If you want to push this block this way, you apply force, right? This block sliding against the ground, and there is a friction here. So there's a friction here. What's going to happen? This friction also try to do work. Like you move the block from here. You apply the force, so you're going to say is work done equals to force time distance cos theta. Here in cos theta, theta equals to 0 because you're applying the force this way, and friction is also applying, the displacement is also applying the distance in this direction. So F and D both in the same direction. So here you're writing Ft cos 0 degree, and then answer would be Ft, Ft. Now let's take a look on the other side. Since you're going to move this object from this to this, friction is going to apply a force this way. Friction is against your motion, right? When you try to move, friction work against you, which is going to be other direction. I'm going to call it Fr. Maybe FF. FF means force of friction. This force of friction also going to be with you during this whole time when you're pushing this block against this floor. So friction will be with you during the whole time. It means friction also doing some work. I'm going to call F. WF means work done by friction equals to F D. Right? D is the distance. Friction is going to cover the same distance, but D is like here applied force. And then cosine. In this case, force in this direction, distance in this direction, the angle between the two is 180 degree. So you're going to be writing 180 degree. If you substitute 180 cos 180 equals to minus 1. So when you solve this, guy is going to be equals to F D with minus sign. Why? Because well, this is mathematical, and logically what's happened, since you apply force on this direction, you're doing work in this direction. You're doing work in this direction. This friction force working in against you in this direction. So really, if you're pushing the block this way, you're doing 10 joule of work. Maybe in the end, you're going to be applying 10 joule and friction applying here 2 joule. So 10 minus 2, the answer will be the only work done is done 8 joule. That is why when you want to be moving against friction, you have to double up work. The first work you do to move, which is this one, and the second part of the work you have to do this one to overcome the friction. So bottom line is that if I have any block, I have to move this way. This block need, let's suppose, 10 joule of energy, but there is a friction in the system, might be 2 joules. So really what you have to do 10 joule of work plus 2 joule of work extra, because extra work is going to be overcome the friction. So this guy is waste. What you cannot live without it. Friction is friction. What you gonna do about it? Sometimes using different kind of lubricant in the machines, right? Like you put in oil in the car to reduce the friction, but it's not gonna be going. It's gonna be there. How are you gonna be writing this? Work is done by the force of friction plus work is done by actual equals to delta A. This is total energy. We can also write this one maybe in a little bit expanding the mechanical energy part. This is the work done by force minus work done by friction equal to mechanical energy final minus mechanical energy. Don't forget mechanical energy means what we discussed in the beginning, which is, we can write also this expression like this. And K E F plus kinetic energy final minus potential energy final plus if I have any spring in the system, spring also has the energy. So this equation, what I'm writing, is a global equation. It can be applied anywhere you have energy system, right? And basically, this is a global equation. It can be applied any problem you have potential energy, kinetic energy, spring energy, and friction. It can be applied anywhere. And the last thing we're going to be talking about is what is power. Power is nothing but is the rate of change of energy, right? Rate of change of energy. So really, power equals to delta E over delta. So this can also write E equals to D E over. This is called average power or instantaneous power. Right? Let's take a look another problem. Let's take a look some problems so we can understand these concepts a little bit better. Okay. In this problem, really what we have here, let's talk about this. Read the problem. In a single frictionless roller coaster, frictionless is the key here. The car mass is given, 825 kilogram, top on a first hill with the speed of yes. So they are here. See, there's a car here. It's moving with 17 meters at a height of 42 meters. So this height is given 42. How much work is done by the gravitational force? Gravitational force work actually means potential energy due on the car from point. Bunch of cars are given from point to point A. So this car is going to go from here to there. How much work is done against the gravitational energy? So this is the G, gravitational force towards down. How much work you done from this point to this point? Here. Not by your car. How much work is done by the gravitational potential energy or gravitational force? Remember, gravitational force is always against you. And they have a three different locations from here to there. Second part B, from here to point B. The third part is from here to point C. If the gravitational potential energy of the Earth car Earth system is taken to be zero at C. So if let's suppose the potential energy here is zero, right? What is the value when the car at point D, B, and A? You have to calculate from here to there is how much, here to there is how much. So let's do all these parts one by one. The first thing first we're going to be talking about is part A. So I'm going to be from point A, I'm going to be going from this direction. A, my displacement in this direction. But how much displacement? Really, there's no displacement because think about it, the car goes down from here to here. So go from A, from this location to A, this location. It goes down from here to there, and it comes up. So when you add something like T1 plus T2, so this is T1, that is up to T2. So one is minus, one is plus, then the net will be zero. So car does not really net zero in Z direction, in this direction, in this direction. Right. And the angle between the two is your force is downward, your displacement is this way. So really, the delta will be 90 degree. So if you substitute into the formula, W equals to, I'm gonna say WG because it's a work done by gravity, equals to F D cos theta, and F D cos 90 means 0. So everything becomes 0. So in part A, really, you're not doing any work in the Z direction. Yeah. Let's talk about part B. In part B, we're going to be applying the same thing. So we can say WG. And you are going in part B, you're going from where to where? Point B. So basically, you're going from here to here. How? I follow this slide. So really, if you go to this point, how much up and down you travel? You not travel much. You go down, then you go up, then you go down, and you half partially go up. So really, the only thing distance you cover is this, which is h by 2, and this h by 2. So you are here. So really, how much you travel from here to there? This distance, which is h by 2. So I'm going to take this and substitute here. I'm going to call potential energy equals to m g h. Or if I want to write it another way, I can write the same way. The part 1 is done. I write here F D cos theta. Right? Since it's a potential energy problem, I don't have to use this formula. Maybe I can say this FD equal to mgh. I can solve this way. Does the m is given? Yes, m is given. M is 825. What is g? G value is 9.81, sometimes 80. Right? 9.80. This is the value of g. And what's the value of h? H is basically half of h. Because see, you only come from here to there, you only come how much? You only come from here to there. Because here, literally, and you are here, so how much you travel? H in z direction, like in this direction. You only travel h by 2. So you substitute the value, I'll be done. I'm going to substitute everything and we find out. The answer is 1.70 x.5. The unit will be joule. Here the unit will be 0 joules, and joules represented by J. Part C. Right? I'm going to be applying the same thing. WG equals to FG T. Right? And FD means the force in the FG means the force in the gravity direction. Is the FG, sorry. And I can just write mgh again because there's a potential energy formula. That's what I'm going to be using. In this case, I don't have the complete h. You see here, you go from here to there, then come down, then come up, then come all the way down to here. So really from here to up to this point, how much distance I cover? H. So this time I'm going to be using h, not the half. Okay, substitute here. So m is giving 8.5, g is giving 9.80, h is giving 42, I believe, right here. Let's give me the problem right here. Right, it's here, h value is given. Let's substitute everything, and then the answer will be 3.4 x 5 joule. If you notice one thing, it's pretty much double of this. It's double, right? Part D, they're asking, right? Part D, they're asking is D. We need to find the value of the energy at point B and E part A. So the value of energy, so really they're asking if energy here is zero, how much energy is here as compared to that is the difference. Remember, some energy goes down, some energy goes up. So they are asking that. And same thing they're asking about this point in part. So we're gonna do part B and then part. So part D, they're asking the energy equals to UG. UG means potential energy. That's what we need to calculate. And the formula is mgh. But since you go on half of it, this is how much, what is the height? H by 2. So you're going to substitute H value, use H by 2. And you're going to substitute here of H, then 8, 25, then 9.80. I'm going to eliminate this thing and says 825 divided by 2. This is the value is given, H by 2 means 825 divided by 2, and then mass is given, 42 divided by 2. And this is it. We solve this, the answer will be 1.70 x 1.5, which is pretty similar. Look at that. If I go from the top, I got same. If I go from the bottom, same. This is pretty much the same energy. Right. So if you bring the block from up to down, it's the same energy level. Potential energy basically is a level of energy now. Level of energy now. So if you are at point B, it doesn't matter which way you get here, from bottom to top or from here you come. In both cases, you are here. So your UG should be equal in both calculations. That's what you got this. Let's do part E. In part E, we're going to do the same thing. Exactly. The only difference is that you are going from C to A. A is on the top. So I'm going to be doing UG again. And H here, I'm not going to be using half. I'm using A 25 times 2 times 9.80. The answer should be the same answer that what you got earlier in part C. Okay.
Let's take a look at another problem.
In this problem, we do have another scenario in this problem for energy. A pendulum consisting of 20 kg of stone. Pendulum consisting of 20 kg of stones rested on a pendulum. This is 20 kg stone, which is the permanent marker. So there's a pendulum hanging there, stone, swinging with 4-meter string, negligible mass, that is the length of the string. The stone has a speed of this one when it passes to the lowest point. So this guy is going here and it's swinging. When it comes to point here, the velocity is given, which is right here, 8 meters. You need to find out what is the speed when the string is at 60 degree to the vertical. So we need to find out the maybe here I can say this point when the angle is 60 degrees. So this pendulum is going to go all the way down up. The velocity is 0, then come down. And I need to find the velocity at this point when the angle is 60 degrees. What would be the energy of the pendulum or the system? Right? We need to find out. The part C we need to find out if the potential energy of the pendulum or system is taken to be 0 at the stone lowest point. It means if my U value, Ug, which is potential energy, equals to 0 at this point. What is the storm? What is the total energy, total mechanical energy of the system? We need to find out the mechanical energy of the system. Let's solve this. We know all the formulas. First of all, we need to mgh is my potential energy formula, or you can call it U. The question is that what is H? And the way it's going to be working this H is I'm going to be taking this total L from here to there. This L is L, and this guy is 60 degrees. So I'm here. So when I'm here versus here, how much am I? Just this much. Right? I want this guy. How much is that? So what I'm going to do? I'm going to take this L minus this gap, this distance. So L is the total gap from here to there, and this little short distance I'm going to be covered, and this little distance is equals to L cos 30. Right? We know y axis cos 30, cos 60, pretty much. L cos 60. So really, what do I need? I need L minus L cos 60. So that's what I'm going to be writing here. My mgh should be equals to mg L minus L cos 60. I'm going to take L common, 1 minus cos 60. Right? We need to find out the mechanical energy. Mechanical energy equals to E max equals to half. Basically mechanical energy is to be Ke plus E. Potential energy and kinetic energy summation is the mechanical energy. So kinetic energy equals to half mv squared plus potential energy equals to mv L mgl 1 minus cos. What we're going to do, we just need to be substituting the values we do have in this question. And if I solve this thing, we'll be adding half, mass is given to 2, velocity is given to 8, plus 8. No, sorry, m is 2. M is 2. G is 9.8. L is length is given 4. Right, so 4 minus 1 minus cos 60. Solve everything, the answer is 64. Right? And if I says in this system part C, right, this is part B, I can get the answer. So in part C is saying if the energy here is 0, so all the energies moves up is Ke 0. So at this point Ke is equals to 0. At this point the problem says Ug equals to 0. So the difference between the two is the total energy, which is mechanical energy. So I'm going to say as observed in our solution of part A. The total mechanical energy, the total is also equals to 64 because none of the energy is going to go waste anywhere. There's no friction in the system, by the way. Friction is the one who causing the energy to be waste, and there's no friction in the system. So I'm going to do this
Let's take a look another problem.
problem. Take a look. Equally drag its bag's box across the floor by applying horizontal force of, you know, equally drag a bag box across the floor by applying horizontal force of 8 Newton. The kinetic friction acting on the box has a magnitude of 5 Newton. As a box is dragged through that much distance along the way, what is done? Work is done by the cooling applied force and P that increase the thermal energy of the bed and floor, yes or no. So really what is that? It's asking you a pretty good scenario. It is a floor here like this, and there is a box floor, and there's a goalie. We try to push this block, box, red box is going to be coming here. The distance from here to here is 0.70 along the straight line. So there in the straight line. He's applying force by 8 Newton. We apply the force by 8 Newton. There is a kinetic friction in the system. So they are also applying the friction force against this motion. Or Ff equals to 5 Newton. So the part A is what is the work done by the system? And part B is that the bottom of this block or the box is going to be heat up, right? So let's talk about part A. We have this formula. Applied force equals to force times distance and cosine theta. Since force and displacement, like force in this way and distance is also this way, so that cos theta will be 0 here. So cosine 0 means 1. So I'm not going to be writing this out. Force is given, yes, force is given. D is 0.7. So if you multiply them, the answer will be 5.6 joule. Work is applied is 5.7. Thermal energy, right? The thermal energy generated equal to delta E TH equal to F K T, and then 5 Newton over 0.7. You multiply the answer with 3.5 joules. This energy generated because the distance energy equals to friction times distance. That's much energy generated. It means thermal energy generated. Yes. There is a thermal energy increase of the system. Yes. What's happened? The block is actually getting warmer. Okay.
Thank you for watching Knowledge Academy. Please subscribe my channel.